Let's now examine in more detail what exactly we mean by a noisy quantum storage. In this rather abstract class, we will unfortunately not have time to review actual experimental implementations of quantum memories. However, you can find some pointers to the literature in the lecture notes. Instead, we confine ourselves to mathematical models of such storage devices, and using such mathematical models, we can then prove security. Let's start with the most simple example of bounded storage. Here we just count qubits, but there will be no noise. We can perfectly store q qubits for an essentially arbitrary amount of time. If we were the adversary, how could we use such a storage device? Remember that we could perform an encoding and a decoding. So we could take some input state of n qubits and stuff it in our q-qubit memory as best as we can. Note that this encoder should work for any input state, even if we have no classical description of the density matrix. So how many qubits can we store in the q-qubit quantum memory? In other words, what is the rate r between the number of qubits that we want to store and the number of qubits q in our quantum memory? Even the power of quantum computation does not allow us to compress more than q qubits into q qubits, a smaller space. In fact, if n is larger than q, or equivalently, the rate is larger than 1, then no matter what encoder and decoder we use, the trace distance between the input and the output state is larger than 1 minus a term that decreases exponentially with n. So we are doomed to fail if we try to store more than n qubits in a q-qubit memory. Just out of curiosity, you might ask, how many classical bits can we store? Of course, not using the extra classical memory on the side. It turns out that the same is true for classical bits. If we try to store more than q classical bits in the quantum memory, then for any encoder and decoder, the probability that we recover the bits correctly decreases exponentially with n. So now you might be asking, how about if each qubit is also a little bit noisy? In the sense that whenever we input a qubit into the quantum memory, we receive a noisy qubit at the output that is not identical to the input. So what is the maximal rate at which we can send qubits over such noisy devices? The answer to this depends on the noisy channel n. It is given by what is called the quantum capacity. It's different for every n and sometimes very hard to compute. For the noiseless channel of the bounded storage case, for example, the maximum rate was 1. We could store 1 qubit per 1 qubit of storage, but not more. But if this qubit in our storage also has noise, then the rate is typically smaller than 1, or in fact sometimes much smaller than 1, giving a much more accurate estimate on what the adversary might be able to accomplish. For completeness, for storing classical bits, there are of course also limits. The maximum rate at which we can send classical bits is known as the classical capacity of the quantum channel. We will not have time to delve into the subject of channels and their capacities in general here. This would take a whole lecture series by itself. If you're curious about this, and maybe you should be, check out the following book. What will be important for us is something known as the strong converse rate of the noisy channel N. Specifically, if the rate is larger than this magic threshold, then the probability of sending information through the channel successfully decreases exponentially with n. Or, if you want to think about trace distances, the trace distance between the input and the output is exponentially close to 1. To return to cryptography, we thus see the following. If we have q qubits of noisy storage, then if n is only large enough, we can effectively overflow the memory. The fact that quantum channels have a limited capacity says that if n is too large, then there is no encoder and no decoder physically possible that can still protect the information. So the adversary is guaranteed to lose information. Later, we will see how to use this to prove security. For now, let's have a look at some mathematical models of quantum channels. In the context of key distribution, we already saw the bit flip channel acting on classical bits. If we express this as a quantum operation, it would be some map, and let me call it dph, that with some probability r leaves the state rho the input intact, but with some error probability 1 minus r flips the bit. Here I have written the bit flip operation as a Pauli x applied to the input state. Because remember, x takes 0 to 1 and 1 to 0. Of course, this form of noise also makes sense for fully quantum inputs, inputs which are not in the standard basis. It is known as the bit flip channel or as the dephasing channel in the X basis. There's also another popular way to model noise, known as the depolarizing channel. This channel again leaves the state intact with some probability r. But with some error probability, 1 minus r, it replaces the state with a completely mixed state. These are two famous forms to model noise, where especially the first one, dephasing noise, is quite dominant in many physical implementations. It is clear that such mathematical descriptions only approximate the physical reality of quantum memories. Nevertheless, they form useful abstractions, also in the context of noisy storage cryptography. It is useful to know that these models are typically optimistic, and the actual noise will be worse, which makes it safe to use in cryptography. You might be wondering why not just always count the number of qubits. From a classical perspective, counting qubits seems very natural. While this is definitely out of the scope of our class, unfortunately, it is useful to know that there are quantum memories where each element, each qubit memory cell, is actually an infinite dimensional system, infinitely many qubits. Only because their energy limitations or strong form of noise will we nevertheless not be able to store many qubits in that actual memory cell. Hence, in the quantum regime, it pays to consider noisy storage instead of merely bounded storage.